Hello, everyone. My name is Jiaxu Miao, and from the Rally Lab UTS, and Yunchao Wei and Yi Yang are my academic supervisors. Today, I'll introduce our paper, Memory Aggregation Networks for Efficient Interactive Video Object Segmentation. So what is interactive VOS? In one video, the mask of the target object is generated by user annotations, for example, scribbles, at only one frame, and the computed mask is temporally propagated to generate the masks for the entire video. The user can refine the segmentation masks by repeatedly providing annotations until the segmentation masks are satisfied. This picture shows the round-based interactive VOS, round 1, round 2, round 3, and so on. And the interactive VOS includes the user interaction and the temporal propagation. Most previous methods usually use two independent neural networks.
昨天我刚才把那 email forward 给你了，他回来了。那个昨天
two independent neural networks for the interaction and temporal propagation, and the whole neural network has to start a new feed-forward computation in each interaction round, which is time-consuming. And in this paper, we propose a unified, efficient, and accurate framework. Includes three components: the pixel embedding backbone, the interaction branch, and the propagation branch. The pixel embedding backbone uses the embedding encoder to encode each pixel into a pixel embedding. Note that the embedding encoder are only used at the first round, interaction round. In next interaction rounds, we directly use the pixel embeddings extracted by the embedding encoder. This operation can save a lot of time. And the interaction branch aims to generate the mask of the user annotated frame. In the interaction branch, the user provide annotations, these scribbles, and we concat the pixel embedding of the user annotated frame, the scribbles provided by the users, and the predicted mask at the previous round, interaction round. We take the concatenated feature as the input and use interaction segmentation head with 4 convolutional layers to predict the mask. The propagation branch aims to propagate the information from the user annotated frame and previous frame into the current frame. So we need to compute the relationship between the current frame and the annotated frame, and the relationship between the current frame and previous frame. We use two matching maps, global matching maps and local distance matching maps to propagate the information, and we use 2 memory modules to aggregate the local map and global map from the previous interaction rounds. We read the aggregated local map and global map, and we from the memories, we concat the global map, local map, the pixel embeddings of the current frame, and the predicted mask of the previous frame. And we use a propagation segmentation head with 4 convolutional layers to predict the mask of the current frame. Next, I will introduce the matching map and the memory modules detailedly. For each pixel, we can have the pixel embeddings by the pixel embedding encoder. For example, for pixel P and pixel Q, or we have the embedding EP and EQ in the embedding space. We use this formula to compute to normalize the distance from 0 to 1. The smaller number means the distance is closer. So how to compute the global matching map and local matching map? For each pixel in the current frame, we can compute the distance between this pixel and the annotated pixels in the user annotated frame. We use the nearest neighbor as the number of the as the number of the global matching map at this pixel locations. For example, this map is a global matching map, and the number is small at this pixel location. So, so this means that these pixels are closer to the annotated pixels. So these pixels are more likely belonging to the target object. For example, this person. And these pixels, the number of these pixels are very large, close to 1. So these pixels are more likely to belonging to the background. Similarly, we can compute the local matching map between the current frame and the previous frame. Because the previous frame is very similar to the current frame, and the mask of the previous frame is predicted, so it is not exactly correct. Thus, we just compute the distance between the pixel of the current frame and the pixels around this pixel. So this is why we call this matching map the local matching map. So how we aggregate the information from the previous interaction runs. For the global map, we just use the minimum number of the for each pixel in the global memory. For example, in at interaction 1, we have the global matching map. We just put it in the global map memory, and in the at the interaction 2, we have the global map. We compute the we keep the minimum number of at each pixel. So we can aggregate the information for the global matching map. The local map is different from the global map because the local map is calculated between the current frame and the previous frame, and the mask of the previous frame is predicted. So it is not exactly correct. The errors will accumulate during the temporary propagation. So we use the we select the local map. We record the local maps in the local map memory, and we select the local map which is the nearest to the user annotated frame. For example, when we compute the mask of the current frame 12, at round 4, we use the local matching map at round 3 because the annotated frame in at round 3 is very close to frame 12, and the annotated frame at the annotated frame at round 4 is far away from the far away from the current frame. And we use a forgetting mechanism because at the early interaction rounds, the predicted masks are not good. So the local matching map is also bad. So we just use past R rounds to select the local matching map. This is the GIF figure of the two memory modules, and we can see that if R is 2, we just select the local map from past two local maps, past the 2 rounds. And we evaluate our method on Davis validation set, and at that time we achieved the state of the art and outperforms previous state of arts by a large margin. Besides, we do not use any additional information. For example, we do not use the optical flow. We do not use the CRF as the post processing. We do not use additional YouTube VOS training set. And this picture shows some qualitative results. This is the ablation study. This ablation study shows the effectiveness of our proposed global and local memories. This line means we do not use the global and local memory, and this line we add the local memory, we add the global memory, and we add the both global and local memory. And this shows that our proposed memories can improve the accuracy. And this ablation study shows the impact of past R rounds in the local map memory, and we keep past 2 or 3 rounds can achieve the best performance. Thank you. Any questions?
Yeah, so any questions, please raise the hand or you can type your question in the chat. Okay, I have some questions. So you mentioned you have the global map and local map.
Yeah.
So do you provide any initial segmentation results for global map and local map? Or you just directly to do this and then do refinement?
No, this is there is no refinement. It sorry. Wait a moment.
Maybe come back your slide.
During training, it is end-to-end training, and we first train our model. You only use the propagation branch, so the global map and the local map is directly obtained, and there's no refinement.
Okay. But what's the purpose to have local map? So it seems both of them are segmentations, right? So why need to define the global map and local map here?
The global map aims to propagate the information from the annotated frame, and the local map aims to propagate the information from the previous frame, because the previous frame is very similar to the current frame, and we have the predicted mask of the previous frame, so we can propagate the predicted masks to the current frame, and the local machine map is the local machine map is we use the distance matching maps, and this map can propagate the information by the distance. Yeah.
So can we say you can using the local map to propagate the information from global map for the next stream?
Propagate the information.
You have suppose I guess you have the global map, okay, as the training frame, and then you have the local map to propagate the information from previous frame to the next frame, right?
Yeah, yeah.
So in this process, kind of refinement for your segmentations from previous frame to local frame based on the global map.
Yes.
Okay. Thank you.